In this video, we will be finding moments of inertia of circular section. So we'll be finding the moments of inertia about x-axis, about y-axis, as well as about z-axis. Let us say this is the circular area that we are talking about, and here is our x-axis. Let us say here is our y-axis. So let us first find the value of Iz, because that is the most easiest to find. Now by definition, Iz is equal to integration r square into dA, where r is the radial distance of a small elemental area that you are assuming. Let us assume the elemental area like this, having an angle, subtending an angle d theta here and inclined at an angle theta from here. So this is our elemental area dA. Now this elemental area will have a distance here as r, and this distance here will be small elemental distance, that is dr. Coming to this arc length, that arc will have a length equal to r into d theta, and what we see here as the elemental area will be almost equal to a rectangle, almost similar to a rectangle. So the area dA will be equal to length into breadth, the length being r d theta and breadth being dr. When we substitute these values into the equation, we get integration r square into r d theta into dr. Now since there are two elemental lengths here, we have to integrate it 2 times, and of course we have to decide the limits accordingly. So let us divide them into 2 parts. The first we will take for r, so we get r cube dr, and the limits for r are from 0 to a maximum value as let us say capital R, that being the radius of the circle. Next we are left with integration d theta, and theta as an angle we can see here is varying from x to x, that is a complete 360 degrees it is turning. So from 0 to a maximum angle 360, and because theta is appearing individually, we have to take the angle in radians. So 360 degrees or 2 pi radians, that is the angle we have to take. Now let us integrate these. So we get r power 4 by 4 limits 0 to r multiplied with integration of d theta is theta itself, and again the limits are 0 to 2 pi. So when you substitute the limits, we get capital R power 4 by 4 times 2 pi. So this 2 cancels, and we are left with pi r power 4 by 2. So this is our Iz, or the polar moment of inertia. Now we know from perpendicular axis theorem that Iz is equal to Ix plus Iy, and also here in the diagram we know that because the diagram is symmetric about both x and y axis, Ix will be equal to Iy. When we substitute this equation here in the first one, we get Iz equals 2 times of Ix, or Ix equals Iz divided by 2. Now we know the value of Iz. If you substitute that over here, we get Ix equal to pi r power 4 by 2 and multiplied with 2, 1 by 2 of course, half of that. So we get pi r power 4 by 4, this being the value of Ix. And here because Ix is equal to Iy, that will also be equal to Iy. So these are all the moments of inertia for the circle. So we need to remember these moments of inertia formally, and whenever a problem comes up which has circular section in it, we will be using this to find the moments of inertia of the composite diagram.